So before starting the subject, we will start from a basic mathematics that we already have done into high school or intermediate. So this lecture series is basically developed for the BTech or BS Computer Science students which often fail difficulty to understand the subject quantum mechanics into deep. So we will start from the very basic mathematics that we will already have done into high school intermediate, then we will switch to the advanced level gradually. So I start the discussion with a small is a vector v that I can sketch into a Euclidean space. Let's fire some questions on the vector first. Somebody can ask what are I and j. So I and j basically are the bases of the vector. I and j are called the basis of the vector which are over which the vector v is formed. So they are nothing but the unit vector. So I will use this notation to denote the length of the vector, or sometimes into quantum computing literature it is called norm. So I will refer the term norm rather than the term length. So the norm of the vector I is equal to 1 and norm of the vector j is also equal to 1. It means the length of the vector I and j1. Simultaneously, they also have other property. They are perpendicular to each other. So I start this sketch from the origin O, and this is the vector I, and this is the vector j, which both are perpendicular to each other, and the length of these vectors are unit. So these are unit vectors which are perpendicular to each other, and this system form the basis of the vector v over which the vector v is formed. I can make a detailed sketch here. So Euclidean space. So I am considering the formation of the vector into Euclidean space. Euclidean space. So this is x-axis, this is y-axis, this is the origin, and this is the vector I, this is the vector j, which are perpendicular to each other, and the length of these two vectors are unit. They have unit length, and so I can sketch now very easily 3i. 3i means the vector I is amplified by the amount 3. 3 is a scalar quantity. So I can move 3 steps further along the x-axis. I can amplify I by the amount of 3, and I can reach to the point P, that is 3i. So from the O to the point P, that is the vector quantity OP, and it is 3i. Similarly, for j, j is a vector which is amplified by the scalar amount 4. So I can reach to the point Q from the O, which is nothing but the 4j. J is amplified by the amount 4. So the vector OQ is nothing but the 4j. So I can figure it out the length of these two vectors, or I can say the norm of these two vectors, that is nothing but the norm 3i. Norm has a distributive property. So scalar norm of the scalar quantity 3 multiplied by norm of the scalar vector quantity I, and it is in itself a scalar quantity. It will remain 3 multiplied by the norm of the I. Norm of the I is 1. So 3 multiplied by 1, that is 3. So length of this line will be 3. Length of this line will be 3. I mean 3 unit I can move from the origin to the point P. Similarly, I can find it out the length of the vector OQ, that is norm of the vector for j or length. They are same thing. So it has distributive property multiplied by j. If 4 is a scalar quantity multiplied by j, the length of the j unit vector, that is 1, it is j. So it means the distance from the O to the point P, that is nothing but the 4. So I can move 3 unit amount from the origin and will reach to the point P, and then along the y-axis I can move 4 unit. So here I can reach to this point, that is called R, and I can, this is nothing but the 4, and OP is 3. PR is 4 because PR is equal to OQ, because PR is equal to OQ. The norm of the PR is norm of the OQ, which are equal, that is 4. So I can sketch this vector V from O to R, that is the representation of the vector V. So vector V into the Euclidean space is nothing but the vector OR. Okay, so now can I find out the length of this vector V? Yes, the length of the vector I can find it out by using the Pythagoras theorem. If you will look at here, triangle OPR is a right angle triangle. Triangle OPR is a right angle triangle. So where this angle is 90 degree. This is point P, this is point R, this is point O. So this is 3, this is 4. So I can apply Pythagoras theorem. Easily I can calculate the length of the vector V. That is nothing but the length of OR. So square root of that is 3 square base square plus square root of 4 square perpendicular square. It means square root of 9 plus 16, that is square root of 25, that is 5. Fine enough. I calculated the length of the norm or norm of the vector V, that is nothing but the 5. So this is amount 5. OR distance is 5. So this way I represented the vector V into the Euclidean space. I described the quantities involved in the formation of the vector I and J. I and J are called the bases of the vector, which has properties such that the norm of the vectors I and J is equal to 1 and the angle between these two vectors is always 90 degree. So this system of two unit vectors which are perpendicular to each other forms the basis of the vector V. Basis means there is something over which the vector V is formed. So this system, this is a system, this is called basis, and over which the vector V is formed, or which the vector V is formed. In fact, often every mathematical quantity has bases. So these are the bases of the vector. I and j are the bases of the vector, and 3i is a vector quantity, 4j is a vector quantity. Addition of these two vectors gives another vector, that is v. So I calculated the length of the vector v by using the Pythagoras theorem from the triangle OPR. I also described the system of the bases over which the vector v is formed. Now, so we will learn how to treat the vector in the matrix form. Treating the vector into matrix form, that is very important. That is very important. Treating in linear algebra, treating a vector in matrix form. I take the same example of this vector, that is 3i plus 4j. Now somebody can ask a question that, can I represent this vector in terms of a matrix? Yes, it is very easy to represent the vector in terms of a matrix. So I will sketch a column matrix and I will put this scalar quantity here 3, this scalar quantity 4 here. So it is the 2 by 1 dimensional matrix. So vector v is nothing but the represented into a 2 by 1 dimensional matrix by putting the components of the vectors along the that is along the rows. And so can I calculate the transpose of this matrix into matrix form? Yes, the matrix representation of the matrix is 3 and 4. So transpose of this matrix will be 3 and 4. I mean the row will become column and this row will become other column. So it has one row and two columns. So dimension will be 1 by 2. So the question arises, can we calculate the norm of vector v, that is norm of vector v, by using matrix representation? Matrix representation? The answer is yes. So how to do it? So in the previous example, we just calculated the norm of the vector v by sketching this into the Euclidean space and further by applying the Pythagoras theorem. But here directly we have this vector into the matrix form, and then v transpose quantity we also have. So it is easy to calculate the norm of the vector while the vector is represented in the matrix form. So let's try to do this experiment. I multiply this matrix V transpose by the vector V. Let's see what happens. So this is nothing but 3 and 4, that is 3 multiplied by 4 multiplied by a column matrix, so 3 and 4. So dimension is 1 by 2, its dimension is 1 2 by 1, 2 and 2 match, so dimension will be 1 by 1. So you will get a scalar quantity multiplied 3 multiplied 3 by plus 4 multiplied by 4, that is nothing but the 9 plus 16, that is 25. Fine enough. So we calculated this quantity transpose multiplied by the vector, that is 25. Now I take the square root on both the sides. So what I will get, that is 5. It is nothing but the norm of the vector v that already we have calculated by using the Pythagoras theorem. So we conclude that this expression actually gives the norm of the vector v. This is nothing but the norm of the vector v. So this expression v gives the norm of the vector v. The norm of the vector v is calculated v vector v transpose multiplied by the vector v when v is represented into the matrix form. Now this expression is widely used in quantum computation while we are doing a lot of calculations by using the Dirac-Bell algebra. We will discuss it later. So I have given ample of information about the vector quantity, which already we have done into the high school or intermediate, how the vector is formed into the Euclidean space, what are the bases of the vector, what are the properties of the vector, and how a vector can be represented in the matrix form, and further the norm of the vector can also be calculated by using the matrix form by giving this expression. So thank you.